we're talking about naming hydrocarbons. Hydrocarbons, by definition, is a compound that has carbon and hydrogen. Okay. And we're going to name it by identifying the longest chain, longest continuous chain. Doesn't this have to be straight? So our longest chain, let me see if I can get a different color here. Make it run here. That doesn't look good. There we go. Our longest chain, our longest continuous chain is right here. Okay, there's no other way to get 8 carbons that are connected. Okay, no matter which way we go, that's the longest chain. So that's our base chain. Okay, then we have substituents off of that, and that's how we name it. So the chain is going to be octane, because that means 8, right? Oct means 8, OCT, and ANE means what? What does ANE mean? Anybody remember? ANE means all single bonds. Perfect. Single bonds only. ANE is single bonds. ENE is what? What comes after single bonds? Double bonds. Yeah.
Double bonds?
And YNE is?
Triple.
Triple bonds. You got it. So all single bonds. So it's octane. 8 carbons, all single bonded together. And then there's 2 attachment groups circled in red. There's 1 carbon, that's methyl, because methane is 1 carbon. We drop the ANE and add YL if it's an attachment. And 2 carbons is ethyl, because it's ethane, means 2 carbons. We drop the ANE and add YL if it's an extension. And we put those together. Okay, so we put them together, in alphabetical order. So which one's going to come first? Ethyl, right? Because E comes before M. Okay. We have to number the chain so we know where things are at. You number the carbon chain to give the substituent the lowest possible number. So if we started from this end, this would be 1, 2, 3, 4. There's your first substituent at 4. If we start from this end, 1, 2, 3, our first substituent is at 3. So we start from the right side. Okay, so those are our numbers in blue. So we have our ethyl group is the first one that's named because it's alphabetical. So it's 5 ethyl. Oh, there we go. 5 ethyl, then 3 methyl, then octane. And it tells you what, the name tells you exactly what structure it is. There's no duplicates on the names this way. Every organic compound has a specific individual name. So we can identify it. So 5 ethyl, 3 methyl, octane. There's an ethyl group at 5, there's a methyl group at 3, there's an 8 carbon chain, and it's all single bonds. That's what the name tells you. So far, so good. When there's numbers and letters, there's always a dash between a number and a letter, and there's always a comma if there's 2 numbers in a row. That's the rules. So between a number and a letter, there's always a dash. Between 2 numbers that are together, there's always a comma. All right, let's go to another. Here we'll give some examples here. So names for alkanes. So this is a 6 carbon chain. Okay. And we're numbering it from right to left because our lowest attachment would be 2. If we do it the other way, the lowest attachment would be 3. Okay, so we have a methyl group at number 2. We have an ethyl group at number 4. Because there's 2 carbons and there's 1 carbon. Okay, we have 6 carbons, all single bonds. So what's the parent structure going to be? What's the name of the carbon chain?
Hexane.
Hexane. Perfect. Hex means 6. ANE is double bonds. And I get that's all from that chart in the very beginning of the chapter. We said the methane, ethane, propane, butane, hexane, heptane, octane, nonane, and decane. Okay. That's 1 through 10 for your identification of your carbon chains. So the name of this thing would be 4-ethyl 2-methyl hexane. Okay, so 4-ethyl 2-methyl hexane. It tells you there's a 2-carbon group at number 4. There's a 1-carbon group at number 2. There's a 6-carbon chain, and it's all single bonds. Okay, and there's dashes between numbers and letters. Okay, so hyphenated repeaters are considered when alphabeted. Okay, if there's a die or a try or there's multiple things, we don't count that for our base when we're doing alphabetical order. We'll show you an example right here. So what's the longest chain you can see? Let's see, 1, 2, 3, 4, 5, 6 that way. 1, 2, 3, 4, 5, 6, 7 that way. 1, 2, 3, 4, 5, 6, 7, 8. The longest I see is 8. And that's straight across. This is my longest chain. Can anybody see a longer one?
I see 9 from that elbow.
You see 9? 1, 2, 3.
Can you do the bottom 3 and then up 1 and then everything to the right?
You're right. That is. Let me erase that. Very good. Perfect. I was just seeing if you guys knew. There's 9. Okay. 1, 2, 3, 4, 5, 6, 7, 8. There's 9. Okay. Are we going to count from the top line across or the bottom line across? Which way are we going to go?
Bottom right, CH3 is 1.
Okay. This would be number 1, right? 2, 3, 4, 5, 6, 7, 8, 9. Okay, because that gives our first substituent number 4. The other way, if we number it from the top row, it'd be 1, 2, 3, 4, 5 be the first substituent. Okay, so we go bottom to top when we're numbering. There's our 9-carbon chain, and then we have substituents attached to it. We have this group, and we have this group. Okay, the group on the left is an isopropyl group. So we have isopropyl. Where's my phone? Let me turn this off. Oh, it is off. Get off my screen. All right. So we got an isopropyl. This at number 4 is what's called isopropyl. Okay. And number 5, this was a sec-butyl group. We talked about these a little bit before as their attachments. Propyl is, we look at isopropyl. Propyl is 3 carbons. Iso, like isomer, goes right in the middle of the attachment. So 3 carbons, the attachment dead center is isopropyl. The other group is 4 carbons. You have a first one, a secondary one. So attaching the secondary carbon is a sec-butyl group. Butyl means 4. Sec means attaches to the second carbon. So those are 2 attachments. We have 4 isopropyl, 5 sec-butyl. Okay. Now,
what
we have a
grouping
9.
are you talking about?
The
Ones in the red?
The ones in red.
Okay.
Okay, the ones in red. The one all the way to the left is an isopropyl, because propyl means 3, right?
Mm-hmm.
And iso means attached. So it attaches to the center carbon. So isopropyl. That's what gets that extension, that name. And the other one's 4 carbons. So that's butyl. And it attaches to the second carbon. So it's called sec-butyl. So this attachment right here attaches to the second carbon. And this attachment attaches to the middle carbon of the propane.
Oh, okay, I got you.
There's only about, okay, does that make sense?
Yeah, whatever you were drawing was like really delayed, so I didn't know what sections you were talking about.
Yeah, I'm having trouble with the internet. It's back. It's really getting a problem tonight. For this, it was yesterday the same way. Is it caught up now?
Like yes, I guess.
All right. So what's the chain? The 9-carbon chain. What's the name of the chain?
No name.
nonane. NON means 9. ANE means single bonds. So we put that together. Now, when we're doing alphabetical order, the prefixes don't count. So this is propyl and this is butyl. Okay, that's where we go by for our names. The second iso or prefixes, they don't count. Neither would di or try anything like that. Okay, so butyl's the first one. So it's 5-sec-butyl, 4-isopropyl, nonane. That tells you exactly what it is. So that's our 9 carbons. Let's know it's going to number it just the same way we did. Okay, it's going to give you one extension, one substituent, the other substituent. And it's going to be, that didn't do good. See if we can get this all to go here. Sometimes it advances too fast on the screen here. Yeah, let's count our 9 carbons again.
It's SECO or
It should
SEC?
produce. What's that?
SECO or just SEC? Oh, never mind. Sorry, I see it on the bottom.
Yeah, on the bottom it's a lot clearer. So it's 5-sec-butyl, 4-isopropyl nonane. Okay, so we have when you're doing organic chemistry, you always go backwards. So you see you have nonane, you have 9 carbons, and number 4, there's an isopropyl group, and number 5 is a sec-butyl group. Okay, so if we had, let's draw one out, let's see if everybody can do this. Let's draw CH3, C bonded to CH3, bonded to CH3, bonded to C, H2, CH2, CH3, CH3. Let's do a simple one here. CH2, CH3. All right. Did that come through okay?
Yeah.
Okay, perfect. So what's our longest carbon or longest continuous carbon chain?
7.
7. There's our longest continuous carbon chain. Are we going to number that from left to right or from right to left?
Right to left.
Right to left. Maybe. Or why?
Is that what you said to do?
No. I said you number it so you give it the lowest number to the first substituent group. Where's our
Left to right.
Left to right. Where's our substituent groups? Let's use green here. This is a substituent group.
Yes.
This one's here. This one here. Those are hanging off the chain. So if we label it from left to right, the first one comes at number 2. If I label it from right to left, the first one comes at number 3. Which way do we label it?
Left to right.
Left to right. 1, 2, 3, 4, 5, 6, 7. All right. So let's write out what those are. 7 is what? What's a 7 carbon chain, all single bonds?
Heptane.
Heptane, right? HEP.
Yes.
T is 7. A and E is single bonds. So there's our chain. Now, what do we have attached to it? We have 4 methyl groups, right? And where are they at? We have 1 at 2. We have 1 at 2. We have 1 at 5. We have 1 at 5. Okay. So how many methyl groups are there? There's 4. So it's tetra.
4.
Because you said where it is and how many. Tetra. Methyl. Okay. Commas between numbers. Dashes between numbers and letters. You always have to say the number of substituent groups you have. We have 4, so it's tetra. Tetra means 4. And then they're all methyl groups. So now I put it together. So the name of this thing would be 2, 2, 5, 5, tetra, methyl, heptane. Right? Does that make sense? Let's just kind of make sure everybody understands where we're at. Okay. It's 2255. You tell us, you have to tell someone where everything's attached, how many there are, and the type of attachment, the longest carbon chain, and if it's all single or double or triple bonds. That's the basics for it. Now we get more complex after that. Because once you get double bonds, triple bonds, you gotta say where they're at or functional groups. So you need to understand the basics. This is the basics for naming organic compounds. This is a IUPAC nomenclature. International Union of Applied holy cow. You want to blank on the name for chemistry? I'll figure it'll come back to me. I need to get a little sticky for this one. International Pure and Applied Chemistry. Okay. So any questions on that? That's the basics. That's what you have to understand. And then we're going to build on this. So are we good with this so far? Or do we need another example?
Can we do another example?
I can make up another example. Perfect.
Thank you.
No problem. If I can erase this. Not an easy way to erase all that, but let's go to the next one. It's erasing my letters. Yeah, the internet here really has a delay to it. Okay, let me see if I can put another blank screen here. Let's do this real quick. Let's say copy. Let's see if I can paste it in. Paste. Let's go back. All right, got another blank screen. Okay, so let's make up another one. Let's go, let's say CH3, CH2, 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 CH3. Oh, that can't be a 2. I can't erase on this, can I? Or I can go like that. There we go. We'll just do it in white. Okay. So CH, CH2, CH, CH3, CH, CH2, CH3, CH2, CH2, CH3. And let's do one more to change on that. Let's say that is CH. Let's do it this way. And CH3. How's that look? Okay, let's name this thing. What's our first step?
Finding the longest carbon chain.
You got it. Perfect. What's the longest carbon chain? One. What's the other you got? 1, 2.
8.
I get 8. Let's do this. Here's our longest chain.
Yes.
Okay. Everybody see that as the longest chain.
Yes. Does it matter if you were to take like that as opposed to the second two? It's the same length.
Say that again.
So that the longest chain is 8, but there's different, I guess, ways of putting it. Because you could have taken
Okay.
like the bottom CH3, or you could have taken the 2 from the second constituent.
Yep.
Does it matter?
Nope, doesn't matter. As long as you got the longest chain, it does not matter. Okay, so let's do this one. You can do anyone you want as long as you get the longest chain. And are we gonna start from the left or start from the right?
The left.
Start from the left. That gives our substituents lowest numbers. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. And our substituents, we have a group coming off here. We have a group coming off here, a group coming off here, and a group coming off here. So far, so good?
Mhm.
Okay, so what are the groups? We have, let's name that. What's the chain? What's an 8 carbon chain, all single bonds?
Octane.
Octane. Oct means 8. A and E is all single bonds. Okay. Let's name the methyl groups. What numbers are methyls at?
Two and four.
2 and 4. Perfect. So 2, 4, and there's 2 of them. So it's dimethyl. Di means 2. And the ethyl groups are 2 carbons. Where numbers are those at? Where are my ethyl groups at?
3 and 5.
3 and 5.
3 and 5. Perfect. So 3, 5, and there's 2 of those 2, diethyl. And we put those, now we put that together. So you have three parts, now I put them together. Okay, alphabetical order. The prefixes don't count, so the dyes don't count. So this is methyl, this is ethyl. Ethyl comes first. So it's 3, 5, diethyl. Okay, 2, 4, dimethyl. And it's octane. Okay. That's the name of the compound. Now, if you're going backwards, if I gave you the name, you had to write the structure. A and E is single bonds, oct is 8. So there's 8 single bonds connected. You go to the number 2 and number 4, there's a methyl group. Go to numbers 3 and number 5, there's an ethyl group. So everything's labeled right out for you. Okay. So the International Union of Pure and Applied Chemistry. So those are IUPAC names for alkanes. Okay. So when a branch occurs more than once, we have to tell you how many times it occurs. Di means 2, tri means 3, tetra means 4. So if I have tripropyl, there's 3 propyl groups attached. If I have tetramethyl, there's 4 methyl groups attached. You have to tell me where they're at and how many there are when you write the name. Okay, so you list the number of carbon branches for that substituent to the name with a separate number for each occurrence. In other words, you're going to have, if you have 2 methyl groups, you get to tell me where they're at. Are they at number 3 and number 4? At number 2 and number 4? Are they both on number 2? So you have to tell me you have dimethyl, there's 2 methyl groups, and they're at number 3 and number 4. Okay. Or you can have triethyl groups, which means there's 3 ethyl groups. One at 4, another one at 4, another one at 6. Okay. And ethyl is 2 carbons. commas between numbers, dashes between numbers and letters. You have to tell me where, you have to say, you have to know the longest carbon chain, longest continuous carbon chain. Okay. You have to know all the substituents, the numbers they're at, and how many of each substituent occurs when you group it. That's it. That's how you name things. Okay. So let's name the following compound. Let's look at that. Where's the longest carbon chain?
Down the middle.
2, 3, 4, 5, okay. 7, right?
Yes.
Okay, there's your 7 numbers. They're all flying up there. Everybody see the 7 blue numbers?
Yes.
Perfect. Yeah, let me know, because sometimes the computers will lag and it won't make sense what I'm saying. So how many substituent groups do we have attached to that chain?
3.
3. Perfect. We have 2 of the same group here. Let me see if I'm going to mark these anyways. Yeah. Okay. We have 2 of the same group and 1 of a different group. So we have 2 methyl groups and 1 ethyl group. Where are they at?
2 and 3 and 5.
Yeah, 2 and 3 are your methyl groups. So it's 2, 3 dimethyl and then 5 ethyl. Let me see what I wrote here. Okay. So at number 5, right here, there's an ethyl group, 5 ethyl. At 2 and 3, there's a methyl group. So 2, 3 dimethyl. Okay, 1 ethyl group, dimethyl group. Okay. Remember, the prefixes don't count for alphabetic order. So even though this says di and this is a D, that doesn't count for your alphabetic order. What counts is your attachment, your substituent, which is a methyl group.
So the name of the
So it's
longest
5
chain is
ethyl,
always
2,
last.
3 dimethyl. Yes. Name of the chain is always last. It tells you it's 7 carbon chain heptane. All single bonds. Okay. I think there's more examples to come, so don't panic. All right. This one's kind of complex. So what's our longest carbon chain here?
And
Yeah, I get 10. Okay. There's our carbon chain. So 10 carbons. Okay. What's the name of a 10 carbon chain that's all single bonds?
Decane.
It is decane. Perfect. It's decane. And look at our substituents. Let's mark our substituents. There's our carbon chain, and this is what's coming off of it. Okay. So we have got, let's break them apart. Let's go each one individually. So look at the methyl groups. How many methyl groups do we have?
2
2.
2. Perfect. And where are they at?
at 3.
3.
And 3.
3. So our methane goes 3, 3, dimethyl. Okay. What else we got attached? What other kind of group?
Ethyl.
Ethyl group. And that's at what number?
6.
Okay. We got a 6 ethyl. Okay. And what's the other group attached?
Butyl.
That's a butyl group, but it's isobutyl. It's 4 carbons, and then it comes right through the middle of that, the 3rd chain. So that's an isobutyl group, and it's at number 6. Like I said, there's only like 3 or 4 of those groups that are, you have to learn that we recognize the names of those. So isobutyl. And that's it. Then we put it together. We have a B for butyl. We have an E. We have an M. So we have the alphabetical order. We put that together. Comes out to 6 isobutyl. Okay. 6 ethyl. 3,3-dimethyl decane. We just place them all in alphabetical order and put kind of what we've established. Now, if you forget how to name this group like here, there is another way to do it, because this is a propyl group attached and the methyl group attached to that. So it would not be wrong to put the 6 belongs down here rather than right there. This didn't come down. You could put 6-ethyl, like we got, 3,3-dimethyl. And at number 6, you could put a 2-methyl propyl, because here's your propyl group, 1, 2, 3 carbons. And at number 2, it's a methyl group. So you continue to name it within parentheses like we did the other groups. So you can see it both ways. This is the most common way right here, the top line. But if you forget what isobutyl is or sec-butyl, and you draw on a blank kind of quiz or a test, you can name it the other way and it still will be right. Okay? It just follows the same rules. Is this starting to make some kind of sense?
Yeah, it is.
All right, perfect. Because this is the hardest part. Once you get this down pat, then we apply this to everything else. We're going to build on it. Draw the structural formula for 1-bromo-4-methyl-hexane. Begin by running the 6 compounds for formula of each carbon. Add the substituents. All right. Let's just take this as one step at a time. So we're going to draw 1-bromo-4-methyl-hexane. Now, you can have substituents that aren't carbon groups, like the halogens. Halogens are bromine, chlorine, iodine, and fluorine. And their names of substituents is fluoro, bromo, chloro, or iodo. Okay, and in the same exact way we do it with carbon substituent groups. And we'll do it the exact same way, and I'll show you. So the structural formula for 1-bromo-4-methyl-hexane. What do I tell you in organic chemistry? Work which way?
Backwards.
Work backwards. Organic chemistry is always backwards. Okay, so start on the right. Okay, 1-bromo-4-methyl-hexane. You know what hexane is, right? What's hexane?
6.
Seven a carbon.
And they're all what kind of bonds?
Yeah, single bonds.
Single bonds, because the A and E. So put 6 carbons. 1, 2, 3, 4, 5, 6. There you go. At number 4, put a methyl group. So let's just make 1, 2, 3, 4. We'll put a methyl group. Methyl is 1 carbon. And at number 1, we're going to put a bromo group. Bromo is bromine. So Br. That's it. Then fill in hydrogens everywhere else. So it's bromine. So we got CH2. We can put Br out here as an attachment. That's fine. CH2, CH2, CH, CH3, CH2, CH3. 1, 2, 3, 4, 5, 6 carbons. And that's your structural formula. Now, to be a lot clearer, once I do it this way, there's 6 carbons. We have the methyl group attached and the bromine group attached at 1 and number 4. Go back. Okay, so there's your structural formula. Just put hydrogens at every line. And that's your structural formula. Now, I can show you how to do line formulas. We talked about that a little bit before. There's a carbon every bend, which is so much easier to do. And that's what everybody usually does. And you'd be expected to do line formulas for the test and structural formulas. So you want, let's just work backward. Hexane is 1, 2, 3, 4, 5, 6. There's hexane. So count the ends and every bend. Everybody see there's 1, 2, 3, 4, 5, 6 carbons. And number 1, we put a bromine group. 2, 3, and number 4, we put a methyl group. That's it. That's all you gotta do to draw it. Because at the end of every line, there's a carbon. Every bend is a carbon, and there's our Br group on number 1. So much easier to draw line formulas. So much easier to see them.
So the assumption just made that there's hydrogens there to fill the bonds with carbon.
Correct. Every place there that you need 4 bonds to make carbon, you put a hydrogen. Like up here, there's a carbon, and it's because that's the end of the line. So there's 3 hydrogen. So that's a CH3 group because every carbon has
okay.
to have 4 bonds. Okay. And line strength makes it so much easier. You don't write all the hydrogens in. We'll start doing those for each one of these as we do around here too. So draw the structure formula for 1 bromo 4 methyl. That was the thing we just did. So here's our condensed formula. Okay, that's our structural formula. And there's the condensed. This is what it looks like as your condensed formula. Okay, so those are 3 types of formulas you need to know. Structural formula, which is this one. This is your structural. This is your condensed. And the other was the line formula. Okay. And again, that's 1 bromo, 4 methyl hexane. So we're now working backwards. We're naming we're drawing it from the name. Okay. Okay, so now we got structural isomers. We talked about isomers before. Okay. The same molecular formula, different structural formula. Okay. So you have the same number of carbons and hydrogens. Okay, but they have a different arrangement or a different IUPAC name. Okay, so let's do butane. Butane is 4 carbons all in a chain. Isobutane is an attachment of a carbon, okay, right in the middle of the 3 carbon chain. Again, each one of those is C4. This is C4, H10, right?
Yes.
Okay, and this one is C4, H10. Same molecular formula, different structure. Okay, so they're different shape to them. Okay, so there's different physical properties. They don't behave the same. Even though the same molecular formula, that didn't look very good. There's an H. Okay, they have a different structural formula. Okay, so what's the line formula for butane? Butane would be 1, 2, 3, 4. That's it. That's butane. What's the structural formula for isobutane? There's 3 carbon chain, 1, 2, 3. And off the center one, there's a CH3. That's isobutane. That's the line formula for them.
Okay, so the one on the left
Very
has
simple.
3 lines.
What's that?
The one on the left, I thought you said it should be 4 lines, but it's 3.
It's 3 carbons. Remember,
Oh,
there's a
3
carbon here. Remember, every end is a carbon. So there's 1 carbon here, 2 carbons.
Oh,
three carbons.
okay. Sorry.
Oh, no, you're fine. That's why I asked. No, I like questions. So here's 1 carbon, 2 carbons, 3 carbon. That's this chain right here. And there's that methyl group attached. That's your 4th carbon right there. Okay. And look at the different properties. Butane has a boiling point of minus 0.4. Isobutane has a boiling point of negative 12. Melting point minus 139. Melting point minus 145. So different physical properties. Okay, even though they're the same molecular formula, because they have different shapes and they bond differently and attach differently because of that. Okay. So if you look at butane, you see it's 1 long chain. Okay. Isobutane is broken up. So the boiling point for isobutane is lower, okay, because it's broken up. It doesn't have the same amount of London dispersion forces we talked about before of those weak interactions that hold it together. Once you start putting the chops in the chain, it doesn't stick together as well. What is the IUPAC name of the molecule below, which is commonly called Freon? Freon was Freon 12. We don't use Freon in our cars anymore in our products because of the ozone, effects on the ozone. But this is Freon. That's what it looks like. It's a chlorofluorocarbon, CFC, which is aerosol propellant. It was used in a lot of hairsprays, things like that, back in the 90s, okay, before it's banned. It's not been manufactured in the United States since 1995 because it's CFC damage to the ozone layer. Chlorofluorocarbons are destroying the ozone layer. It's still propellant in asthma inhalers like albuterol. So when you have a patient that uses albuterol for asthma, You push that down. What propels the albuterol out of that inhaler is a chlorofluorocarbon. Okay, and this is what it is. It's Freon 12. So this is Freon 12. You can see the picture of it. What is the name of that compound? What the IUPAC name, like we've been naming? Okay. What's the longest continuous carbon chain?
1.
1. What's 1 carbon?
Okay.
Someone said it. Methane. Methane's 1 carbon. And we have attachments. We have chlorine attached, which is chloro. So we have it. And where is it at? Is that
1.
number 1? Because it doesn't have a choice. There's your number 1 carbon. Okay. And there's 2 of it, number 1. So it's 1 di chloro. And you have fluorine attached. Can you guess what that one is?
1.
1 di fluoro. And you put it together. Alphabetical order, which would come first, the chloro, the fluoro?
The chloro.
Fluoro. So there's your number 1 carbon. Those are your 4 substituent attachments. Okay. And the name is 1,1-dichloro, 1,1-difluoromethane. Now you can drop the ones if you want, because there's no other choice. If it's dichloro, difluoro, methane, and there's only 1 carbon, I mean, here's your methane. Okay. 1's redundant. You can put it or you can leave it off. Either way is fine. It's just like in the formulas, in molecular formulas, chemical formulas, we always leave the 1 off because there's only 1. There's only 1 carbon. There's no other place it can be attached. So it's 1,1-dichloro, 1,1-difluoromethane, or dichloro, difluoromethane. Either way is acceptable. All right. Okay, name the following molecule, which is a component of the tsetse fly pheromone. Molecules of this are used as attractants in tsetse fly control measures. Everybody know what a pheromone is? Pheromone is a very small molecule released by an insect or other animal that attracts the opposite sex, usually released by females. We use them all the time in insect traps. We put the female pheromone in the traps and the males flock to it like crazy. Okay, that's what pheromones are used for, to attract the opposite sex for reproduction. All right, so we look at this thing. What's our longest carbon chain?
17.
17. There's 14 of them here. There's 14 here. There's 1, 14, another one, 14, 15, 16. There's 17 across. Okay. And we're going to count left. We're going to count right to left, because the only substituent we have is that methyl group right there. That's our substituent. So to give it the lowest number, we're going to start from the right-hand side. Okay. So it's going to be 2-methyl, and then it's going to be heptadecane, which is 7 plus 10. Okay, which gives us 17. So 2-methyl. There's a substituent, a methyl group number 2, and then hepta 7, deca is 10. So 17. So 2-methyl heptadecane. Making sense?
Yeah.
Perfect. All right. What is the IUPAC name of the following molecule? Standard of excellence used in determining the octane rating of gasoline. So when you get 98 or 93 or 94 octane, this is the molecule they're measuring at the gas pump. Okay, they're putting in a sensor and they're measuring this molecule. It determines your octane rating. People keep trying to, my phone never rings. All right. Okay, so what's the longest carbon chain?
5.
5. If it's 5, why do they call it an octane rating?
Because there's 8.
Perfect, because there's 8 total carbons. It's an isomer of octane. But this is when they use to determine the rating to see how pure the gasoline is. This is how they rate your gasoline. And you have 3 attachments to that 5-carbon chain. All right. So what's the name of the 5-carbon chain? What's 5 for carbons?
Is it peptane?
Pentane, right? Like a pentagon, five sides. So it's pentane. Okay, that's the name of the chain. How many attachments are there? What are they and where are they at? Got to tell them that. So what numbers are the attachments at?
2, 2, and 4.
Perfect. 2, 2, 4. There's one at 2, there's one at 2, and there's one at 4. Then your dash. How many are there?
3,
3. 3 is tri. And what type are they? What are the attachments?
methyl.
Methyl. So put that together. 2, 2, 4, trimethyl pentane. You got it. Commas between letters. Commas between numbers. Dash between numbers and letters. Everything else you just put right together. You guys got this. Making a lot more sense here. All right, determine the IUPAC name for each of the following. So here's our structural formula. And this one we're going to do a little bit differently, but let's count. What's the longest carbon chain?
Eight.
Perfect. There's 8. There's your 8 carbons. How many attachments we have?
2.
2. Okay, so 8 carbons is what name?
Octane.
Octane. And our attachments are at what numbers?
2 and 4.
2, 4, and it's dimethyl. Okay. And just put that together. 2, 4, dimethyl octane. Now, if you got a piece of paper in front of you, I want you to draw the line format for this one too. Then I'll show you how to do it. We'll double check, make sure you can do that. Because you do start drawing line structures for these things. We'll give you just a couple seconds. It doesn't take long to draw line structures. All right, so to draw the line structure, this is what you should have on your paper. You draw the line, the longest carbon chain. Should have 8 carbons. So 1, 2, 3, 4, 5, 6, 7, 8. There's 8 carbons. And then you want to put a methyl group, which is 1 carbon at number 2 and at number 4. There it is. That's the line structure. Everybody see how to go from this to this. But you're going to have to do that for the exam.
Yes.
Okay. It's just a nice, easy way to draw things. And this is what you see. This is what we'll be drawing most of the class. Okay. So 2, and you can name this just same way as naming them. All right. This is a little bit different than than Freon, but still a chlorofluorocarbon. Still destroys the ozone. So what's our longest carbon chain?
1.
1. So what's the name? What's the name of 1 carbon?
Methane.
Methane. And what are attachments?
All at 1.
All at 1. What type are they? What's the F?
Fluoro.
Fluoro. What's the Cl?
Fluoro.
Fluoro. And the chlorine is it's trichloro. We put 1, 1, 1 in front of it, or 1 in front of those, but you don't really need to with only 1 carbon. So we put it together, we have trichlorofluoromethane. 1 carbon, 4 attachments. Why did I go backwards? We already did that one. There we go. That's where we're at.
So is
One
are you able
carbon
to do a line formula
and
with
our
something
4
like this with just some methane?
Yeah, you can do a line formula. You can always do a line formula. It's
So
trichlorophenol.
how would
It would
that
look
work?
like
Because
this.
I thought at each end is a carbon.
It is.
Oh,
Each end and each junction. There's your 1 carbon in the center. There's your 4 attachments. You thought you could trick me, huh?
no, I thought you were gonna trick me on the test.
But there's your 1 carbon right there, because
Thank
the
you.
carbon is at every bend, every end, every intersection. There's always a carbon, and there's your 4 attachments to it. So there's your line
So
structure.
if we do a line formula for this one, do we have to label what the other molecules are at the end?
Yes, because if there's no labels here, if this wasn't here, that would be a carbon.
Right. Okay.
There's not 2 carbons. So you're absolutely right, 100% right. You have to put the chlorine and the fluorines at the end to show that those are not carbons. Okay. Anytime the only thing you assume when something not there is hydrogen. That's the only thing you leave off. Anything else you have to put on the structure. So if I asked you how many hydrogen atoms are there in a typical test question would be, how many hydrogen atoms are there in trichlorofluoromethane?
0,
Huh?
0.
0. That'd be the answer. There's 0 hydrogens. Perfect. Everybody see why this is the line structure?
Yeah.
What's that?
So on a test, like on a question like that on the test, if you ask us like how many hydrogens are in trichlorofluoromethane, are you going to give us like any type of the formulas for it?
What do you mean?
Like, is it just going to be like the word that's on the bottom of the
Yep.
picture, or is it going to be the drawing?
You get to do the drawing to figure it out.
Okay, so we need to know how many like electrons that they're going to be sharing.
Right. You have to know how carbon always bonds to 4. Can't bond to more than 4.
Okay.
And it might give you, it's gonna be multiple choice. It might be like 1, 2, 3, 4, 5, or none of the above. You put none of the above because it's 0.
Okay.
Now I'll give you some more difficult ones. Like if you drew out like 2-methyl hexane, how many hydrogens are in there? Then you got to draw it out and understand how many hydrogens you have. Okay, so that's an indication that you know how to draw the structure correctly. Because I can't make you draw the structure because it's all online. Okay, but I can ask the questions in such a way that you have to draw the structure correctly so you can answer the question. So once you learn how to draw these things, you'll be able to answer any of the questions I asked as long as you draw it correctly. Okay. So determine this thing. What's the longest carbon chain here?
7.
Pick 7, right? And why did I put my numbers from right to left instead of left to right this time?
Because the substituent is closer to the right end.
Perfect. Because the substituents, you have to get the substituents, which are these here. These are your substituents. You have to give them the lowest possible numbers. So this way they're 2, 3, and 4. If I went the other way, it would be 4, 5, and 6. So 2, 3, and 4 is lower than 4, 5, and 6. Okay. So this is a 7 carbon chain. So what's the name of the carbon chain?
Heptane.
Heptene, right? Heptane, A-N-E-N-D, all single bonds. At number 4, we have what?
4.
Fluoro. At number 3, we have what?
Wow.
Chloral. At number, where are we at? Number 2, we have what?
Methyl.
Methyl. Okay, so in order we have 3 chloral, 4, 3 chloral, 4 fluoral, 2 methyl heptane. Putting it together, you get C, F, and M in alphabetical order. And there's at number 3, there's a chlorine group. Number 4, there's a fluorine group. And number 2, there's a methyl group. And it's 7 carbons, all single bonds. And that's what's in the name. Okay. So a test question will say, how many hydrogens are there in 3 chlorofluoromethyl, 2 methyl heptane? You've got to draw it correctly to tell me how many carbons there are, and then you count the carbons. I mean, hydrogens. I would ask how many hydrogens. That we know how the bonding works. And the line structure for this would be 7 carbons. So 1, 2, 3, 4, 5, 6, 7. That's a peak there. It's not a line. And then number 2, there'd be a methyl group. So there's 2, put a methyl group there. And number 3, there'd be a chlorine group. And at number 4, there'd be a fluorine group. That's it. And you could draw it left to right, however you want to do it. You could draw it from the right side also. So it's everything you can say, because you flip it around in space, it rotates in three-dimensional space. Okay. Questions so far?
This is probably an obvious question, but how do we determine how many hydrogens are in the heptane group? Like if we didn't see
Okay.
it.
You draw out the compound. In other words, I'll give you this name
Uh-huh.
and you draw this structure. Okay. And then you count the hydrogens. So you got 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 in the first row. And you got 3 up here. So there's 16 total. You have to draw the structure out.
Mhm.
And then once you draw it out, then you just count the hydrogens. But if you don't draw it correctly, you won't know the number of hydrogens. There's no way of knowing how many hydrogens until you draw it out, because you have to see the bonds and see what's connected. Remember, every carbon has to have 4 bonds. It
Mhm.
bonds to all your structures, and then everything else gets filled with hydrogen. So if you draw the structure correctly, you can tell me how many hydrogen there are in it.
Right, the bonds. Okay, that's what I wasn't thinking of. Okay.
Right.
It's a
Every
lot
carbon-
easier to see with the structural formula.
Yes.
Mhm.
It's easy to do a structure formula. Just got to remember, every carbon has to have 4 bonds. And that determines, once you write all your structures in your substituent groups, put hydrogens everywhere else.
Right. Okay, sounds good.
Make sense? Okay. Draw the structure for 1-bromo-4-methyl-hexane. Structural formula. So working backwards, we have hexane, which hexane means what? Tells you 2 things. What does it tell you?
6.
Bonding
6.
6 carbons
Single
and
bond.
Single bonds.
perfect. 6 carbons, all single bonds. It says there's a methyl group at number 4, and there's a bromo group at number 1. So that's all you have to draw. Now the line structure, let's do that first, just for fun. Hexane is 6 carbons, right? 1, 2, 3, 4, 5, 6 carbons. At number 1, there's a bromine. I can go up or down either way. There's our bromine group. And number 4, 1, 2, 3, 4, there's a methyl group. There's our line structure. Okay. Drawing out our other one, there is 1, 2, 3, 4, 5, 6. This is our structural formula. And number 1, there's a bromine. And number 3, there's a methyl. That's it. That's all you got to do. Just remember, always work backwards. When you're given a name, start at the end, draw your carbon chain, and just add your substituents to it. Okay. 1-bromo-4-methyl-hexane, right? The condensed form, we just did that. Oh, the condensed formula. So they had the structural formula. So the condensed formula is going to take the bonds away. Okay. So there's the bromine at number 1. There's 3 CH2 groups, a hydrogen. And remember, every parentheses goes back to this carbon. So the CH3 group attached there, and CH2, CH3. And this CH2, this bromine is attached to this CH3 group here. Okay, so there's your condensed formula. So you got to write condensed, line, and structural formulas. So condensed formula, you just take the lines away and squish them together. And our line again would be 1,4-methyl-hexane. Hexane is 1, 2, 3, 4, 5, 6. 1 bromine, and there was a number 4-methyl. That's it. There's your line formula. That's a little bit drawn out better there.
So then I thought that the structural formula also the one where it's like let's say it's CH2 and then has a line to Br, but also the one where you just put like all your carbons out and then you give a line, you just automatically put 4 bonds and then fill it in from there. Are those equivalent?
That's the structure formula, correct. Let me go back to this. What am I going back to? Oh, that really went back far.
They're together on the same slide at 10.2 alkalines. It's like way earlier in the chapter. Or like
Yeah,
8
it's
slides
the-
back or something.
Yeah, my computer went way back on this for some reason. I don't know why it did that. Get caught up again here. One. This was it. 1 bromo formula. Okay. Yeah, this is the line for the, okay, this is our line formula. And the structural formula was where you went bromine, CH2, CH2, CH3. Is that what you're saying?
Yeah, so there's that one, and then the other one where you just have like a C, and then you show every single bond. So it's like C, and then there's a line for hydrogen, line for
Okay,
hydrogen, line for bromine. Is that equivalent to that's there?
Same thing as this. It's the exact same thing as this one right here. I'm just putting the H's together rather than putting the H's out.
Okay, so we won't be marked it. Okay,
No. You could do it this way if you makes more sense to you. Hydrogen, 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 CH3, like that, you mean?
Yeah.
These are the exact same thing. Those are equal to
Okay.
each other.
Awesome.
They just put people don't like to draw hydrogens everywhere. So make CH2, CH3s. Okay, so these are structural. This is your condensed, and this is your line formula. Now don't get confused with line formulas because this is at the end of a line. There is no carbon there. Okay. If there's a Br or a Cl or an iodine or something else is there, that takes the place of a carbon. So this is your first carbon. Okay, even though this line continues, this is the attachment number 1, 2, 3, 4, 5, 6. Okay, so if there's nothing at the end, that's a carbon. That's a carbon. If there's something at the end, that's your attachment. Okay, a lot of people count this as the first carbon, and it's not. That's just a bromine attachment to the number 1 carbon, which is right there. That's why when I do it, I draw a line straight up rather than at an angle. That way people tend to notice it's a bromine, not an attachment to the line structure. But just don't get confused on that part. Draw the structural formula for each of the following. 1 bromo, 2 chlorohexane. Okay. So what are we going to draw? We're going to draw how many carbons in a line?
5. No, 6. Sorry.
6, right? We have 6 carbons. And number 1, we're going to put a bromine, and number 2, we're going to put a chlorine. So this is a structural formula. So this is number 1, 2, 3, 4, 5, 6. So you do 6 carbons, and number 1, we placed a bromine, and number 2, we placed a chlorine. 1 bromo, 2 chlorohexane. Again, working backward makes it so much easier. Now let's draw the line structure. Hexane would be 6, 1, 2, 3, 4, 5, 6. And number 1, there's a bromine. And number 2, there's a chlorine. Okay, again, Don't get confused at this end right here. There's no carbon. That's our bromine. This is carbon number 1. And there's our bromine attachment. Number 2, there's a chlorine attachment. All right, pentane. Pentane is how many carbons?
5.
5 carbons. 1, 2, 3, 4, 5 carbons. And number 2, there's a methyl group, right? And number 3, there's a methyl group. That's the line structure. Okay, but drawing the structural formula, we have 5 carbons. Okay, you see the 5 carbons, and at number 2 and at number 3, there's a methyl group. Remember, you have to tell me what number of carbon they're attached to and how many there are. So you're telling me at 2 and 3, and di means 2 methyl groups on a pentane chain. 1, 3, 5 trichloroheptane. Okay. So how many carbons are you going to draw? What's your carbon chain?
7.
There's 7 carbons. And numbers 1, you're going to put what?
Chloro.
A chlorine group. And number 3, chloro, is the number chloro group. And number 5 is going to be chlorine. Everything else is hydrogens. You can make lines, or you can put like CH3, CH2, CH, CH2, CH, CH2, CH2. I know that's not real clear, but you can write it clearer than that, just like that. You put your number 1, number 3, and number 5 chlorine groups, and it's your heptane, 7 carbons. Making sense? 3 chloro, 5 iodo, 4 methyl octane. All right. So how many carbons are you going to have?
8.
8 carbons. So right, I'll just write an 8 carbon chain. 2, 3, 4, 5, 6, 7, 8. And number 4, what's going to be there? What do I put at the 4th carbon?
Methyl.
Methyl, which one carbon, right?
Mhm.
CH3. And number 5, what do I put?
Iodine.
Iodine. And at number 3, what do I put?
Chlorine.
Chlorine. And everything else is hydrogens. That's it. So how it would look like would be CH3, CH2, CH, CH. This is number 1 carbon, number 2, 3, 4, 5, 6, 7, 8. There's your octane. And there's your 3 attachments. 3 chloro, there's a 4 methyl, and there's a 5 iodo. And put them in alphabetical order. So far, so good.
Yep.
All right, perfect. Don't worry, we'll make it harder. Don't worry. All right, working backwards. How many carbons? Butane is how many carbons?
4.
Butane is 4 carbons. That's lighter fluid. Okay, butane. So you have 4 carbons, all single bonds. That's what it tells you. It tells you at number 3, there's what?
Chlorine.
Chlorine. And this tells you at what? What does 1,2-dibromo mean?
That there's a bromine at 1 and 2.
Perfect. Perfect. That's it. You guys got this. So there's your 4 carbons. At number 1 and number 2, there's a bromine group. At number 3, there's a chlorine group. Everything else fill in the hydrogens.
Do we have to put that bromine first? Like if we put it above like the other bromine and the
Put it
chlorine,
like-
is
put it
it
like
gonna be
this.
wrong? Yeah.
Nope, you can do that just fine. That's perfect. That's probably what I would do too. Just because it looks more uniform that way. Yep. You can put it anywhere, or you can alternate. You can put one down, one up, one, alternating them. As long as you put them on the
Bromine
right
would be
carbons,
like that.
that's right. On the right carbons, you're in good shape.
Okay.
What's that thing? Trifluorochloromethane. How many carbons?
1.
1 carbon. And attached to this carbon, you have what?
Fluorine, chlorine.
How many of each?
1 chlorine, 3, 4, and
Perfect. 1 chlorine, 3 fluorines. Oh, I went backwards again. Computer does not like me for some reason this today. There you go. One carbon, 3 fluorines attached, and 1 chlorine. Could you put 1 chloro, 1,1,1 trifluoro
yes.
methane? Yeah, same thing. Exact same thing. But if there's only 1 carbon, you don't have to put it because it's got to be on the number 1 carbon. Okay. All right. As you saw earlier, what's that? Is that a question? No. As you saw earlier, there are 2 arrangements of atoms represented by the molecule C4H10. Okay, butane, you have butane and 2-methylpropane. Okay, those are your isomers. Okay, isomers are the same molecular formula, different structural formulas. So different physical properties. Okay, so these molecules have the same molecular formula, but different arrangements are constitutional or structural isomers. Okay, their structures are different. Isomers are the same number of carbons and hydrogens or anything else, same number of elements. Structural, there's different structural. Okay, those are isomers. Those are called structural isomers. Isomers, these structural isomers are unique compounds because their structures are different. So they have different physical and different chemical properties, different melting points, different boiling points, different hardnesses, and they react differently. Okay, they're going to react to different halogenations and different things we're going to talk about in a little bit. They're going to have different chemical reactions because they're a different shape. Everything works by shape. Okay, how it gets around it. Okay, the difference reflect the different shapes of the molecules. Okay, when we get into enzymes and biological molecules in the body, everything reacts because of the shapes that they make. Okay, that's how whole body's keyed to. So drawing constant structural isomers, write all constant isomers for the formula C6H14. Okay, so you can write a whole bunch of different isomers by rearranging, giving different branch structures for 6 carbons and 14 hydrogens. Okay, the first one is hexane. 1 carbon, 6 carbons, and hydrogen. Okay, so C6H14. Okay, does that have 6 carbons and 14 hydrogens? Yeah, right? 6 carbons, 14 hydrogens. Can we draw that differently? Sure we can. We can draw one there. We could put a methyl group at the number 2 carbon. Again, we have 1, 2, 3, 4, 5. So that's pentane. And then the 6 carbon is the methyl group. And if you count the hydrogens, we still have 14 hydrogens. We could put one in the number 3 position. We could put them as methyl groups at number 2. We could put the methyl group at number 3. Okay, they're different compounds. Now, could I put the methyl group here at the number 1, 2, 4th one for a different isomer?
No,
Perfect. Why?
because it can
Because it's the
be,
same thing as the original one.
It's the exact same thing as this one, to spin it around. Because remember, we put the number of the lowest constant, so this would be 2-methyl pentane, if I put it right there, not 4-methyl. Because it's the same thing as this one in 3-dimensional space, just spin it around. So that one wouldn't count. So those are 2, so far I got 3 isomers. Okay, we could do that. We can make the 1, 2 shorter and put it at number 2 and number 3 methyl groups. Again, this is butane. This would be, this one here is 2,3 dimethyl butane. The other ones were pentane was the longest carbon chain. Okay. But again, it's C6H14. It's a structural isomer. And we could do it. We could put 2 of them on the number 2 carbon. What's the name of this compound right here? Someone just give me the name.
Dimethyl. I forgot what 4 is.
Butane.
Butane,
Perfect.
dimethylbutane.
They said you put, 2,2-dimethylbutane.
Okay.
Yep, perfect. Good, very good. And there's your isomers. Again, if I move these over to here,
Okay.
it would still be the same compound. So those are all isomers. They're all physically different structures. So they all behave differently. They're all going to have chemical reactivity that's going to be different because of their structure, because their shape's going to be different. Okay. Heptane is very poor fuel, given a 0 on the octane rating scale. Doesn't really we put that in your cars. So gasoline octane determined by engine by comparison with 2,2,4 trimethyl That's the standard for octane ratings. And heptane, which is your poor quality. Draw line formulas and give the IUPAC name for each of the 9 isomers of heptane. So heptane is C7H16. Okay, that's heptane, right? So there's 9 different isomers you can draw for heptane. We're going to draw those out and then name them according to the IUPAC nomenclature. Okay, so our first one is going to be heptane. Line structure. 1, 2, 3, 4, 5, 6, 7. 7 carbons. Okay, all the rest hydrogens. 16 hydrogens. Okay, because there'd be 3 hydrogens here, right? There'd be 2 here, there'd be 2 here, there'd be 2 here, 2 here, 2 here, and 3 there. Add them up. That should be 14. 16, I'm sorry. C7H16 is the molecular formula for heptane. Okay. That's the first isomer, and that's the line structure for it. Okay. And that's the name that is heptane. Okay, the next one. Okay. We're going to put a CH3 group on there. And this is the line structure for that one. Okay, again, we just moved the methyl group down 1. So this is a 6-carbon chain. So we still got 7 carbons, 1, 2, 3, 4, 5, 6, 7, and still got 16 hydrogens. What's the IUPAC name for this one? So what's our longest carbon chain? Is 6, right? So 6 change is hexane, 6 carbons, all single bonds. And what's this attachment right here? What's this group called?
2-methylhexane.
Perfect. That's a methyl group. And it's number 2 position. So the name, like you just said, is 2-methylhexane. Perfect. It tells you there's 6 carbons all on a line, 1 single bonds. And at the number 2 carbon, there's a methyl group. And it has the same molecular formula as C7H16. So there's 2 out of the 9. We can move that methyl group to the next one over here, which we will do just like that. And we'll move the methyl group 1 over. There's your line formula. What's the name? It's not number 2 anymore. It's at what number?
3.
3. Perfect. So 3-methylhexane. Now, if I were to add like a bromine right here, how many carbons would you have?
5.
You have 5 in the chain, right? So don't get confused just because there's an N there. If something else is here, that means there's not a carbon there. Okay. Next one, we could put 2 methyl groups together and give you line structure similar to that. Okay. So name that one now. How many carbons in your longest chain? That's where you always start.
It's 2, 2, dimethyl hexane? Or
Not
no,
hexane,
it's 5.
Peptane.
Heptane, yeah.
pentane. Perfect. Perfect. You have 5 carbons in your longest chain, so it's pentane. All single bonds, 5 carbons. And you have methyl groups at 2 and 2. So it's 2,2 dimethyl pentane. Commas between numbers, dashes between numbers and letters. You tell me the location, you tell me how many there are, you tell me the substituent group, and you tell me the base name and all single bonds. That's what all those things mean. Just logical sense with that. Okay, or you can put 2 methyl groups separate from each other. Add one up there. So again, find our longest carbon chain. 1, 2, 3, 4. So it's a 4 carbon chain.
Butane.
Butane, perfect. So what are our groups attached? Tell me the numbers.
2, 2, 3.
Perfect. 2, 2, 3. Then we have how many? We have 3. So it's tri what?
Methane.
Methyl.
Methyl.
Okay,
Methyl.
we drop the N, put the Y out, went to substituent. Perfect. 2, 2, 3 trimethyl butane. Got it. Okay. Or you can move the other one and put the methyl groups in between, closer to each other. Okay. Something like that. We can have one at 2 and 3. Right. So what's the name of this thing?
Two, 3 bimethyl heptane.
Pentane. 5 carbons.
Okay.
1, 2, 3, 4, 5. So 2, 3 dimethyl pentane. Okay. Was that wasn't 9 yet, was it? No, I think it's 2 more. 1 or 2 more. Or you could put the CH2, CH3s together. And you can do it like that. Now what do we got? We got 1, 2, 3, 4, 5. So it's still pentane because they're all single bonds. But now we got another attachment here. Remember, at every intersection and every end, every bend, there is a carbon, unless something else is there. So there's a carbon here and a carbon here. So now we got pentane, which is our main chain. Now we have a different type of attachment. What attachment do we have?
Ethyl.
Ethyl. Perfect. It's a 2 carbon attachment. So it's ethyl. And where's it at? It's at number. What number?
3.
3. So what's the name of this thing?
3-ethyl pentane.
Got it. 3-ethyl pentane. So I can give you something that looks like this on an exam, and you can give me that answer. And I think this is the 9th one, or maybe the 8th one. You can put a CH3 group here and a CH3 group, separate it so the line structure looks like that. And you can always tell isomers because isomers have different names associated with each structure.
2,4-methylpentane.
Close.
Dimethyl.
2,4-dimethylpentane, because you got to tell me where it's at and how many there are. So 2,4-dimethylpentane. You got it. You can tell me the location of each one. You can tell me how many there are. Tell me what the substituent attachment is, and tell me the longest chain and whether it's all single bonds. And this must be number 9, where there's 2 methyl groups attached to it in the center. Okay, so again, our longest carbon chain, 2 attachments to it. What would the name of this thing be?
3,3-dimethylpentane.
You got it. 3,3-dimethylpentane. Here's your 2 methyl groups, and here's your longest chain, and all single bonds, A and E ending. You got it. Those are the 9 isomers of C7H16 of heptane. Okay. Remember, isomers, same formula. Every one of those 9 was C7H16. Every one of them, but they all had different shapes, different structures. That's why it's called isomers. different structural configurations. So you have different chemical and different physical properties. A lot of things exist in nature as cycloalkanes, which means cyclo means a circle, alkane means all single bonds still, just like it did before. All right, so cycloalkanes have 2 less hydrogens than their corresponding alkane chain. So hexane would be C6H14. Cyclohexane would be C6H12. That's because in a chain, if you had hexane, 1, 2, 3, 4, 5, 6 carbons, right? 1, 2, 3, 4, 5, 6 carbons. You have 3 hydrogens on the end, 3 hydrogens on the end, and 2 on every one in between. So you have 2 on every carbon and then 1 on the ends. When you make a chain, and again, we'll draw it C6. There's 6 carbons. Okay. Every carbon, there's 6 points. There's 2 hydrogens on every carbon. You don't have the 2 on the end anymore because you've joined the chain. So now it's C6H12. So to name a cycloalkane, you put cyclo in the beginning. That just means a circle. Okay. You put substituents in alphabetical order, just like you did before. Okay. And if you have multiple substituents, you use the lowest possible set of numbers, just like we did before. You know, you only have 1 substituent, it makes no difference. You don't need to put number 1 there. You can if you want, or you don't have to. It's just assumed it's going to be number 1. Okay, so cyclopropane. There's your line structure. 3 carbons, 1 at every corner. C3H6. There's 2 hydrogens per carbon. Cyclobutane. That's your line structure. 4 carbons. Cyclohexane. 6 carbon. There's your line structure. Okay, you can see structural condensed. There really isn't much of a difference in structural condensed. When we're doing cycloalkanes, you'll be usually drawing line structures with those. Okay, when we name them, we name them by substitution. Okay, we look at the ones below here. Let's look at this side here. This is 6 carbons. Okay, and it's in a cycle group. So it's going to be a cyclohexane. And there's 1 attachment. Here's your chlorine group. So there's one chloro. So the name is going to be chlorocyclohexane or 1-chlorocyclohexane. Doesn't matter because it can be at any position you want. You just rotate that in 3-dimensional space. Okay. So if there's only 1 substituent, you can just name it as chlorocyclohexane. Okay. This next one here. This next one here is 5 carbons. And there's 1 substituent group. Okay. So it's going to be cyclopentane. Pentane is 5 carbons. All single bonds, 5 carbons, cyclopentane. And there's a methyl attachment. So it's going to be methyl cyclopentane. So this tells you there's a methyl attachment. This tells you it's a circle to connect. This tells you it's 5 carbons, and this tells you it's all single bonds. Okay. So name the following. How would you name this thing? How many carbons?
6.
6 carbons. So it's a
2, 3.
hexane.
Yes. Hexane.
And it's in a circle, so it's a what?
Cyclo.
Oh,
Cyclohexane. And there's a chlorine attachment, right?
Yes.
So chloro,
Chlorocyclohexane.
hexane. Perfect. Perfect. I don't want to put that one there. Okay. So this one here. Okay. How many carbons in the circle?
5.
5. Okay. This is just when we did long chains, was how many in the continuous chain. Now this is going to be in the circle now if you have a cyclical one. So there's 5 carbons. Okay. So what would the name of this thing be?
Cyclopentane.
Cyclopentane, and one attachment.
Oh,
Methyl.
Methyl.
yes.
Methyl, cyclo.
Methylcyclopentane.
You got it. Perfect. All right. How many carbons on this one? You count all the angles. 1, 2, 3, 4,
7.
5, 6. Perfect. 7. So what's the name of this structure?
Chlorocycloheptane.
Perfect. Chlorocycloheptane. Means there's a chlorine attached. It's in a cyclical structure of 7 carbons with all single bonds. Okay, this one.
Methylcyclopropane.
Perfect. Is it methyl
Sorry.
attachment? Oh, you got it. That's perfect. Methyl cyclopropane. Okay, 3 carbons in the circle, methyl attached to it. All single bonds. Methyl cyclopropane. What's that one look like?
Ooh. Butane.
Right?
Ethyl cyclobutane.
You got it. Ethyl cyclobutane. Ethyl attachment, 4 carbons in a circle, so ethyl cyclobutane.
Oh, yes.
Okay. Name this one.
So,
Would it be difluorocycloheptane?
hexane.
A and E ending. Hexane. But you got it. Difluoral cyclohexane.
Oh, yes.
It'd be hexene if it was a double bond. Hexane is single bond. So this tells you don't need to put it, it's only at one attachment, so you don't need to put the number. But so it's difluoral, 2 fluorines, cyclical structure, 6 carbons, all single bonds. Difluorocyclohexane. You got it. Now, since we have a ring structure, that means we can lock things in place. In other words, all the ones you've dealt with so far, all the single bonds, they've all been rotate freely in 3-dimensional space. Now I got a ring. A ring locks it. Once these things are attached to a ring structure, you can't move in relation to each other. So now we got a structure that's fixed in place. So we can have what's called cis-trans isomers. Okay? All that means is where the substituent groups are located, either on the top side of the circle or the bottom side of the circle or different sides of the circle. If it's a cis relationship, the substituents are on the same side of the circle. They both face up the top part, or they both face down. A trans relationship means they're on different sides of the circle. One's up, one's down. Okay. So like we said, alkanes can rotate freely around that carbon-carbon single bond. Nothing limits the number of arrangements. It can move freely in 3-dimensional space. Once you lock it in place with a ring structure, now they can't move around anymore. They're locked in place. Okay. So all carbons in the string are interlocked with each other. So we get what's called a formation of cis-trans isomers now. Okay, and that's only due to the lack of free rotation because that space is taken up. Oh, come back. So stereoisomers, okay, they have the same structural formula and bonding patterns, but different arrangement of atoms in space. Okay, so these are isomers that have the same structure. Okay, same structural formula, so the same like that, the same structure written out, same molecular formula, but a different arrangement because they're not locked in space now. Okay, so cis-trans isomers are stereoisomers. Okay, and they're different because of the spatial arrangement, because the locking of that ring in space. Here's what we mean. You can see the chlorines are on the same side of the ring. It's a 3-dimensional image. You can see it on the same. So this is cis. So it's cis 1,2-dichlorocyclohexane. And here the chlorine atoms are on opposite sides. One's on top, one's on bottom. So that's trans 1,2-dichlorocyclohexane. Okay, so you have to look at it in a three-dimensional space here. So cis are on the same side, trans are on opposite sides. So they don't convert between one another. It's not easily. Only by breaking a carbon-carbon bond can they interconvert. So you're going to break a bond to switch between cis and trans. So it doesn't happen without energy being applied to the system. Because to break bonds requires energy. And these are cyclohexane because there's 6 carbons on each of these. Okay, and it's 1,2-dichloro. Give the lowest number to the constituents possible. So it's cis 1,2-dichloro on the same side, trans 1,2-dichlorohexane if they're on opposite sides. All right. How would you name and write the complete name for each one? Is this a cis or a trans looking at it?
Cis. No, trans.
Trans, you're right. This one's going up on the top part. This one's going down on the bottom part. Okay, so it's a trans. And then this is a cyclo what?
Pentane.
Pentane.
5 carbons. And it is a 1,2 what?
Dimethyl.
Dimethyl, yeah.
Dimethyl, perfect. There's 2 methyl groups, 1 and 2, getting the lowest number possible. So put it together, it is trans 1,2-dimethyl cyclopentane. Okay. Another one. Oh, this is on the same side or different sides?
Same side.
Same side. These are both facing down. So this is a
Cis.
cis. So this is going to be a cis 1,2-dimethyl cyclopentane. Same name, except one is cis, one is trans. Okay. So is this cis or this trans?
Cis.
This is cis on the same side. They both point up from the ring structure because the ring structure locks it in place. Okay, how many carbons?
7.
7 carbons. So this is a
Cycloheptane.
cycloheptane.
Yes.
And what are the substituents? What numbers are they?
2.
1 and 2.
Wait, no.
1 and 2.
1 and 2.
And then dichloro, right? So this would be cis 1,2-dichloro cycloheptane. Okay. And the next one, cis or trans?
Cis.
Cis, because they're both pointing up. And this is a cyclo what? How many carbons?
3. Propane.
So cyclopropane. And we're at 1,2 what?
Methyl
Is the
cyclopropane.
constituent here and here. Dimethyl cyclopropane. Perfect. So you'd have 1,2. You'd have cis 1,2-dimethyl cyclopropane. So it gives you a lot of detail on that name. Okay, is that cis or trans? This is on top. This is on bottom.
Trans.
For trans. So this is a trans. Okay. And what is the base name? It's a cyclo what?
Butane.
Cyclobutane. 4 carbons. And the attachments are at what numbers?
1 and 3.
Okay, oh, perfect. 1 and 3, lowest numbers possible. 1, 3, and there's 2 of them, so it's di.
ethyl,
Di what? Diethyl. So it's trans 1, 3 diethyl cyclobutane. Okay, so if you look at the name, it tells you exactly what we got. Trans means they're at opposite sides of the ring. 1 and 3 are the attachment sites for 2 ethyl groups. Cyclo means it's in the circle. Butane means it's 4 carbons. And A and E means single bond. There's a lot of information in the IUPAC names. All right, cis or trans?
Trans.
trans,
Perfect, trans. Okay, and it's cyclical cycle, so it's cyclo. How many carbons?
Hexane.
6 carbons, cyclohexane. And there's attachments at what numbers?
1 and 2.
1 and 2. And there's 2 attachments, so it's di. And what's attached?
Fluoro.
Fluorine group, so it's fluoro. So trans 1, 2 difluoro cyclohexane. Perfect. You guys got this thing. All right. Cis or trans?
Cis.
Cis, same sign. Okay. They're at 1 and 2. Okay. The cyclo with 5 carbons, which means what? What's the name of the circle with 5 carbons?
Pentane.
Pentane. Perfect. Cyclopentane. And those are bromine extensions. They're so bromo. So it's 1, 2. It's a, I'm sorry, cis 1, 2 dibromo cyclopentane. Parent chain is cyclopentane. So cis are 1, 2 dibromo, and it's cis. So it's cis 1, 2 dibromo cyclopentane. Okay. You see. Okay, one's up, one's down. We got 6 carbons in a ring. So what's the parent chain? What's the cyclo? Cyclo what?
Cyclohexane.
Cyclohexane, that's your parent chain. Substituents are the numbers, how many there are, and the name would be what?
1,3-methyl.
1, 3, the letter between there. How many methyls?
Dimethyl.
Mhm.
Perfect, perfect. 1, 3 dimethyl. You got to tell me the numbers. You got to tell me how many. So the numbers are 1, 3. How many is di? And the substituent attachment is methyl. And is it a cis or trans?
Trans.
Trans. One's up,
Yes.
one's down. So put that all together. Trans. 1, 3 dimethyl cyclohexane. Perfect. All right. Now, a little different subject. This is again back to alkanes. So they have the free rotation in space. They can move around. What can make different shapes, different what's called conformations of alkanes. Conformation is different only in the rotation about the carbon-carbon single bond. They're allowed to rotate because they're not locked in space like a ring structure. So there's no such thing as a cis-trans isomer for an alkane, for a linear alkane, because they can rotate in three-dimensional space and they can't get locked in. So one can't go up and down relating to the other. So 2 conformations of ethane and butene are shown below here. Okay, this is ethane, this top one. Butane's the bottom one, 4 carbons. Okay, the first is what's called the staggered form. That's the most stable. It allows hydrogen to be farther apart and it's less crowded. So you can see your hydrogens when it's staggered. If you look at the 3-dimensional model, there's a hydrogen here and there's 2 to the side. So they're not in the same plane close to each other. So this, you have staggered form and you have the eclipsed form. Eclipsed are when it rotates and the hydrogens come close to one another on the top. So the distance here is close. And again, if you have atoms, okay, so they all have electrons floating around, flying around them, right? So they're negative charges around each atom. Negative charges repel one another. They don't want to be close. So it pushes them towards this staggered conformation where the atoms are not stereo hindering each other, not close enough. Okay. And you can have with 4 carbons too. You can have the staggered form, okay, where you have come down, up, down, where they're away from each other. Okay. Or you can have the eclipse form when they come into close contact with each other. The staggered form is always more stable. It's more energy favorable, okay, because it's not forcing the hydrogen atoms to be close to one another. Is that making sense? There's allowed to rotate 3 dimensionals, but some configurations are more stable than others. Okay. And it's staggered makes a more stable configuration. So cycloalkanes also exist in different conformation. Only exception is cyclopropane. It only has 3 carbons. Cyclopropane is always going to be planar. Okay, but the bonds can still rotate in a cyclical pattern as long as there's more than 3, because they can put you at different angles. Okay, so the conformation of 6-membered rings, they're cyclohexanes. That's the one that's always studied, because these are important biological molecules like benzene, glucose. All these are 6-carbon rings. Okay, so everybody studies these, and they've come up with different configurations that these rings take on in space, even though they're ring structures. Okay, so glucose, this is when we study a lot of. That's our blood sugar. Okay, that's the most important sugar in the human body. Okay, it's absorbed by cells of the body and broken down to provide energy for the cells, provide ATP. So glucose produces ATP in the body. Okay, it's a 6-membered carbon ring. It's what you measure when you take if you take your blood sugar in the morning. That's what you're measuring, your blood glucose. How much sugar is in your blood? Okay. The most energy favorable conformation is what's called the chair conformation. Okay. I'm not going to try to draw it. I can draw, but it's never any good. So we'll let the computer draw it for me and draw them on the computer. The hydrogen atoms are perfectly staggered. Remember, eclipsed are staggered. If they're staggered, they're more energy favorable because they're not pushing close to each other. Okay, they're as far apart from one another as possible. Remember the Vesper configurations, valence shell, electron pair repulsion. That's what we did in Chem 3. We determined what the configuration was because how the atoms push away from each other, because they're all negative. Negative charges repel one another because they all have electrons flying around them on the outer shells. Okay, so the hydrogen atoms are described according to their position relative to the ring. Okay, the ones that lie above or below the ring are said to be axial. Those are your axial hydrogens. Okay, they're either at an angle above or below. Okay, the ones that lie in the same plane as the ring are said to be equatorial atoms. Okay, so you have the chair conformation, which is going to be more stable than what's called the boat conformation. We'll show you how to draw both of those. If the hydrogen atoms lie above or below the ring, they're called axial. If they lie in the same plane of the ring, they're called equatorial. Okay, so here's a chair formation. Chair formation looks, I'm a terrible artist when it comes to this. That's your chair formation. Those are your 6 carbons. 1, 2, 3, 4, 5, 6. And the boat formation is when they kick up to each other. So you can see this interference right here between the hydrogen atoms. There is none here because this part here and this part goes down. So this is the chair form. You can see how it lines up and dips down. This is a boat form. Both sides come up. Okay. So the chair form versus a boat form, the chair form is more stable because it does not stereo hinder the atoms as they come in close contact with each other. It's pushing them farther apart, which makes it more stable. Okay. My diagram is good enough to explain it? Not really. All right. This is a chair formation. If you look at the red lines, those are the hydrogen atoms that are above or below the plane of the cyclical structure. You can see hydrogen atom number where it's carbon number 1, hydrogen atom goes up. Number 2 goes down, 3 goes up, 4 goes down, 5 goes up, 6 goes down. They're staggered, which is stereochemically favorable. Look at the blue lines. The blue lines are the hydrogen atoms that are in the same plane as the ring. They go to the side. They're not up or down. So the red lines are your axial hydrogens. The blue lines are your equatorial hydrogens. So axial hydrogens are above or below the plane. Equatorial hydrogens are in the same plane as the ring structure. And this is a chair structure. If this were a boat, this end right here would swing up, and then you get interference between these two. Okay, so your chair formations are more stable. Boat formations are least stable. The axial hydrogens are either above or below the plane. The equatorial hydrogens are in the same plane as the ring structure. Make sense? Someone give me
Yes.
a hand up or something, or a yes.
Yes, it makes sense.
Okay. Perfect. Okay, what structure is this? Chair or boat?
Boat.
Boat, because this is, if this is the chair, this would be down. Okay. Now look at the hydrogens. Nothing's up and down. Everything's at different planes. It is not a stable structure. Okay. It does exist at times, but it's more, the most stable one is the chair formation. Okay. But you still have axial, equatorial. Axial still goes down. You see these going down, these going down, 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 down. Okay. These are in the same plane, the blue ones. Your axial and equatorial hydrogens. We have talked about alkanes and cycloalkanes. Okay, hydrocarbons, carbon and hydrogens exist in many forms. The two we talked about so far, alkanes and cycloalkanes. They can be oxidized. When we talked about oxidation numbers the first day, we're going to review that a little bit. They can be reversed by burning in the presence of excess oxygen, and that's called combustion. Whenever you hear the word combustion, it means in the presence of oxygen. So on the reactant side of the equation, it's going to be plus O2. That's molecular oxygen. Oxygen is always diatomic. So whenever you have to balance an equation, oxygen, when it combusts, is always O2. It is never O. Remember, all the gases on the periodic table are diatomic, except the noble gases. They don't react with each other or anything else. Okay. So when it reacts with oxygen, it's called combustion. When it reacts with a halogen, it's called a halogenation reaction. Halogens are fluorine, chlorine, bromine, and iodine. Okay. So an oxidized reaction is combustion. That means plus O2. When it reacts with a halogen, it's plus F2 or Br2. Remember, halogens are gas room temperature, so they're F2, Br2, Cl2, and I2. The halogens are always diatomic also. All right. So two types of reactions: combustion reactions plus O2, halogenation reactions plus the halogens. All right. So alkane reactions. Okay. Combustion reactions, complete combustion is C4 plus any hydrocarbon plus oxygen goes to CO2 and water. That's complete combustion, carbon dioxide and water. When something combusts completely. So when your body burns, metabolizes glucose, which is a hydrocarbon, it's going to give you CO2 and water. Incomplete combustion, like your automobiles, your motorcycles, okay? They're not efficient engines. They're not designed to be. They're designed to use gas. The hydrocarbon plus oxygen goes to carbon monoxide and water, okay? So if carbon dioxide was released from cars, you would not get carbon monoxide poisoning. You got asphyxiation. This is incomplete combustion. It produces carbon monoxide and water. Carbon monoxide is a poison because your red blood cells in your body carbon monoxide has a high affinity for the red blood cells where oxygen binds. Okay. It has a stronger affinity for your red blood cells than oxygen. So if carbon monoxide is in the air, it binds to your red blood cells and prevents oxygen from binding to those red blood cells. So your body cannot deliver oxygen, even though there's oxygen in the air. Okay. It's not irreversible. It says it's irreversible. It's not irreversible. It's just a higher bonding. It can be reversed by putting the person in, just taking them outside where the carbon monoxide was contained, taking outside, getting them fresh air. Eventually, the carbon monoxide will wear off if you get to them soon enough. But if you don't, it's going to kill them because carbon monoxide binds stronger to the red blood cell. Now, why carbon dioxide isn't a problem? The red blood cell has different binding sites. Okay, so where CO2 bonds is not where oxygen bonds. So they don't compete for the binding site. Carbon monoxide has the same shape as an oxygen molecule. Carbon dioxide is different. So carbon dioxide will bind to a different part of the hemoglobin of red blood cell. And that way the red blood cell can still carry oxygen. Carbon monoxide binds to the binding site of the oxygen molecule on the red blood cell for hemoglobin. And therefore the red blood cell can't combine with oxygen. That's why carbon monoxide is so dangerous and so toxic. Okay. So complete combustion of a hydrocarbon, combustion, once you see the word combustion, you know it's plus O2. Complete combustion of a hydrocarbon is carbon dioxide and water. Incomplete combustion, again, combustion means oxygen, but if it's incomplete, it's going to go to carbon monoxide and water, CO plus H2O. Everybody understands the difference. The human body is a much more efficient machine than an automobile or motorcycle. Okay, they release carbon monoxide and water because it's incomplete combustion of octane, which is your fuel. Right, combustion reactions, adding oxygen, and there's different sizes, carbon 1 through 4. So methane, ethane, propane, and butane are in the gas form. Okay, like a butane lighter is gas, propane is gas when it burns, methane gas, okay, they're used for heating and cooking. Gasoline is C5 through C12. That's used for your motor fuel. Kerosene is C12 to C16. Heating oil, C15 to C18. Lubricating oil, C19, C20. Grease, C18 and up. Wax, C20 and up. Pitch or tar is extremely high. Okay, we'll use that for roofing, things like that. Okay, so the properties change as the number of carbons in the hydrocarbons increase. They go from a gas, okay, to a liquid. Here's your gas, these are your liquids, and it goes to solids. Okay, so they stick together more as the number of carbons increase in the chain. They have more of these London dispersion forces that hold them together. Okay, balance equations. Here we go. Your favorite thing. Write a balance equation for the complete combustion of hexane. We should all be able to do that. We know what hexane is. Okay. When I give you this test on a quest, I'll give you like 2,3-dimethyl cyclopropane. What's the complete combustion? So now you got to figure out the number of carbons, number of hydrogens, and put them in a formula. So hexane is C, what?
6.
C6, H14. Combustion, when you see the word combustion, it means you're adding what?
Oxygen.
Oxygen, which is O2. Oxygen is always diatomic. And complete combustion means you're going to produce, go back. Okay. What are you producing in complete combustion?
CO2.
CO2 plus water. There's your equation. Okay. The words you're looking for are hexane, which is what you're starting with, combustion, which means you're adding a burning presence of oxygen, and complete, which means it's CO2 and water. If it was incomplete, it would be carbon monoxide and water. Okay, so things combust in the presence of oxygen. They need oxygen to burn. There's one compound, okay, that does not require oxygen to burn. And that's called thermoplastics. It's very highly controlled by the United States government. It is not readily available compound. It will burn without the presence of oxygen. So it can burn underground. It can burn all kinds of things, okay, with no oxygen present. We found thermoplastics in the 9/11 towers. Remember when that stuff was burning underground for like 2 weeks later? The ground was still red hot when they were excavating them from the towers from the damage. There was thermoplastic that was burning. Okay. And the United States controls most of that. That's not really available to anybody else. All right, so complete combustion. So there's your equation. So C6H14 plus oxygen goes to CO2. What did I tell you to balance last in this equation? Anything that's by itself. So oxygen is itself. It's not combined to anything else. Say that till the end. Okay. So let's balance this equation. I have how many carbons on the left side?
6.
6. So what do I have to do on the right side? I got to put a 6, I see an arrow there, in front of the CO2. Okay. Now my carbon's balanced. I have 6 on the left, 6 on the right. How many hydrogen on the left side do I have?
14.
14. So I got to make the other side say 14. So I put a 7 in front of the water. The order's going off a little bit on this. I have to fix it. Okay. Now my carbon is balanced. Now my hydrogen is balanced. Now it's easy to balance the oxygen because that's by itself. So how many oxygen do I have now on the right-hand side since it's been balanced?
19.
I have 19. I have 12 oxygens here, and I have 7 here. So a total of 19. Now, how to make the other side say 19? That's an odd number, and O2 is even. So I put a 19 halves in front of the oxygen. So 19 halves. So 19 divided by 2 times 2 equals 19, right? So this equals 19. And this side equals 19. Now I can't leave it like that. I just use that as an iterative step to show me what I can balance. So now I multiply everything by 2 to get rid of the 2. So I multiply this by 2, multiply this by 2, multiply this by 2, multiply this by 2. So I end up with 2 hexanes, 19 oxygens, 12 CO2s, and 14 waters. And that's my balanced equation right there. That's the balanced equation for the, my pencil. Has to be somewhere. Pencils can't disappear if you drop them. There it is. All right. So that is a complete combustion of hexane. And you will see at least one of these problems on your midterm. So know how to balance combustion equations. You need to know when it says combustion, it means plus O2 on the reactant side. You need to know when it says complete, it's going to produce carbon dioxide and water. Fair enough? All right. Write a balanced equation for the complete combustion of cyclobutane. Cyclobutane. You have to tell me how many carbons, how many hydrogens. Cyclobutane is how many carbons?
4.
4. And how many hydrogens? Remember, cyclobutane looks like this. Right? And there's 2 hydrogens at every corner. So C4H8. Perfect. And combustion means?
plus
You see
O2.
the word combustion, what does that mean? Plus O2. And complete means carbon dioxide and water. Okay, so there's your equation. That's what it says. We get all that from the words. We took our word problem and put it into chemical form now. Now we just got to balance it. So how many carbons on the left?
4.
4. Somebody on the other side say 4 also. Okay. How many hydrogens on the left?
8.
8. So what I put a 4 in front of the water to make that say 8. Okay. Now my carbons and hydrogens are balanced. I'm only left with oxygen. So how many oxygens on the right-hand side?
12.
12. Perfect. There's 8 here. And there's 4 here. So how do I make that say 12? What do I put in front of the oxygen?
6.
Perfect. 6. So I put a 6 in front of it. Where's my arrow? Did it come down? There it is. All right. So this is your balanced chemical equation. Again, 4 carbons, 4 carbons, 8 hydrogens, 8 hydrogens, 12 oxygens. 4 times 2 is 8, plus 4, 12 oxygens. Same amount of elements on both sides, we're balanced. Ethane. What's the formula for ethane? C what?
2.
C2H. How many hydrogens? 6. Perfect. Remember, ethane is 2 carbons, and then everything else is hydrogens. 6 of them. C2H6. And again, complete combustion, add oxygen, goes to CO2 and water. So there's your equation. So we've taken our word problem and put it into chemical form. So let's balance it. How many carbons on the left?
2.
2. So I put a 2 in front of the CO2. That gives you 2 carbons on the right. So now the carbons are balanced. How many hydrogens on the left?
6.
There's 6. So I got to put a 3 in front of the H2O to give it 6 hydrogens. Okay. So now my carbons and hydrogen balance. Now I do my oxygens. I always save the O2 for last because it's by itself. How many oxygens on the right-hand side of the equation?
7.
7. There's 4 oxygens here, and there's 3 here. So that gives me a total of 7 oxygens. So how do I make this say 7? What do I put in front of it?
7/2.
7/2. Okay, that makes it say 7. Now we're balanced. I cannot leave a fraction though. I just use that to help me get it balanced. Now I gotta get rid of it. You cannot leave a fraction in a balanced chemical equation because molecules occur as whole units. They don't occur as fractions. You never get water as H2.5O. It's either H2O or C6, H12O6. There's no halves, there's no fractions in molecular formulas. Okay? So this is just a step in helping us determine how to balance it. So I multiply everything by what to get rid of that fraction?
2.
2. So I multiply this by 2, this by 2, this by 2, and this by 2. So what I'm going to end up with is 2 ethane plus 7 oxygens, 4 CO2s, and 6 H2Os. Ah, shoot. Went too far again. We did hexane already. The formatting of this I have to change. It's giving me too many arrows at once, but that's all right. Okay, so that's our cycle. Boy, that went way back, didn't it? Let's get caught back up here again. Detail. That was ethane. That's what we were working on. We were working on ethane. We balanced our carbons. We balanced our hydrogens. We ended up with 7/2 to balance our oxygens. We multiplied everything by 2. And that gave us 2 ethanes plus 7 oxygens goes to 4 CO2s plus 6 H2Os. That's the complete combustion of ethane. Decane. Decane is, what's the formula for decane? C what?
10.
C10, H. (22). Right? There's two hydrogens on every one, except at the end there's 3. Okay, so we have C10H22. Complete combustion gives you oxygen, and complete means CO2 and water. So there's your equation. So what do you have to do? Balance oxygen last. So 10 carbons on the left. What do we put in front of the CO2? We put a 10. So now we got 10 carbons on the left, 10 on the right. We have 22 hydrogen on the left. So how do I make the right side say 22? What do I put in front of the oxygen? I mean, in front of the water, I'm sorry.
11.
11, perfect. Put 11 in front of there. That gives me 22 hydrogens. Now all I got left is to balance oxygens. How many total oxygens do I have on the right-hand side?
31.
31. I got 10 and 2, which is 20. I got 11 here. So I got 31 total oxygens. Okay, so what do I put in front of this O2 to make that say 31?
31/2.
31/2. Perfect. You got it. Put 31/2. And now we're balanced. But now I have a fraction here. I cannot have fractions. So I multiply everything by 2 to get rid of my fraction. So that was going to be 2 decanes. It would give me 31 O2s. It would give me 20 CO2s. And it would give me 22 H2Os. Okay. Now we have a balanced equation for the complete combustion of decane. Again, if you want to check, carbons are 20 and 20. Hydrogen is 44. Hydrogen is 44. Oxygen is 62. And oxygen is 40 and 22, which is 62. Everything balances. That's a complete balanced equation. Octane, I think this is the last one. Octane is, what's the molecular formula for octane?
C8H18.
Perfect. C8H18. Okay. Complete combustion plus O2 goes to CO2 and water. Let me go back again. We're having some issues here. Octane. C8H18 plus oxygen goes to CO2 and water. 8 carbons, make this side say 8. Okay. 18 hydrogens, maybe this side say 18 hydrogens. Okay. Now our carbons and hydrogen balanced. Now we got to put a number in front of here to balance our oxygens. So I have 16 oxygens here plus 9. So a total of 25. So I got to put 25/2 because that's an odd number. And then I got to multiply by 2 to get rid of that fraction. So this gets a 2, this gets a 2, this gets a 2, this gets a 2. So you're going to have with 2 octanes plus 25 O2 go to 16 CO2s and 18 H2Os. And here's your balanced chemical equation for the complete combustion of octane. So what you need to know for the exam, If you see the word combustion, it means plus O2. If you see the word complete combustion, it means it's going to produce CO2 and water. If you see the words incomplete combustion, it's going to produce carbon monoxide and water. I think that's it. Why did that go back again? This computer's definitely having a hard time. Go back to decane. And then we did octane. And that was our balanced chemical equation for octane. Okay. Halogenation. We'll talk about this for a little bit and then we'll start about 9 o'clock. So halogenation. Halogenation was a combination of a hydrocarbon with a halogen. Halogens are always diatomic, just like oxygen was. So if it combines with chlorine, it combines with Cl2. It combines with bromine, it's Br2. Okay. The halogens are always going to be diatomic, just like oxygen. And it's a substitution reaction. One of the hydrogens gets substituted for one of the halogens. That's what substitution means. You switch one for the other. Okay. Its reaction results in replacement of one group for another. Okay. These are called alkyl halides. Alkyl halides. You say they're alkyl groups, have the YL ending. Now they're alkyl halides or alkanes. And then you have hydrogen halides. So the reaction is important. It converts unreactive alkanes into a starting material we can react to make other products. Okay, so halogenation of alkanes only occurs in heat and or UV light. Okay, it takes something to get the reaction to go. If a cycloalkane and if an alkane and a halogen are just there together, they're not going to react. They need heat and or light for the reaction to occur. All right. So halogenation reaction. This is an alkane. This is our halogen. This is just a basic reaction. Whenever you see an R in organic chemistry, it means another carbon group. Could be methyl, could be ethyl, could be propyl, could be butyl, could be anything. It's just a function, it's just a hydrocarbon group. That's what R means. Okay. So at the end of the R is just your carbon chain. And at the end, you have this CH3 group attached to it. And then X2, X stands for halogens, whether it's Cl, Br, iodine, fluorine, whatever. Okay. When you add light or heat, you replace one of these hydrogens with one of the halogens. Okay. So if you have, I'm going to draw a little bit here, R, C, H, 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 plus X2. Okay, X could be chlorine, bromine, fluorine. One of these X's replaces this hydrogen. They switch. Okay, so you end up with R with one X here instead of a hydrogen, and then H attached to the other X. So the hydrogen that was replaced ends up with the other halogen. So let's back to these and get these out of the way if I can do that. Just want to get a little clearer here. There we go. That's perfect. All right, so let's take methane plus bromine. Bromine is going to replace one of these hydrogens, and this other hydrogen is going to come off and bind with the other bromine. Because remember, bromine is Br2. Okay, so one of them goes and replaces it. One gets bonded to the other hydrogen coming off. So with lighter heat, you get bromine on your methane plus HBr. That's your balanced chemical equation. Okay, so this is bromomethane and hydrogen bromide are the two products from methane and bromine. Okay, ethane. Ethane plus chlorine. Okay, ethane is two carbons. One of the hydrogens get replaced with chlorine. and the other one binds, the other chlorine binds to the hydrogen that came off. So you get chloroethane and hydrogen chloride. Again, one of the hydrogens here was kicked off and replaced by chlorine. The hydrogen that got kicked off bonded to the other chlorine when that bond broke. Okay. And you get cycloalkanes also, okay, in this reaction. And remember, it takes heat or light or a combination of the two to go. So this is cyclohexane. Okay, that's your cyclohexane. 6 carbons. One of the hydrogens is replaced with a chlorine. You can react with chlorine, add in the presence of heat. So you add a chlorine here, and the other one replaces that hydrogen here. So these switch. Okay, where the hydrogen was, it comes off. One of the chlorines replaces it. Where the two chlorines are bound together, now it's hydrogen chloride. So you got cyclohexane combined with chlorine to give you chlorocyclohexane plus hydrogen chloride. Once the chlorine or the bromine are added, these compounds become more reactive and can be used for other products to be made. Okay, write a balanced equation showing all possible products and name them according to IUPAC. The monobromination of propane. Mono means only one bromine is going to be replaced, like we showed you in the examples. So bromination of propane. So what's propane?
Three carbons.
3 carbons. How many hydrogens?
8.
8. Perfect. Plus, what are we adding to it? Bromination. So we're adding Br2. And it's going to produce C3H7 because we're losing one hydrogen, and it's a replacement reaction, replacing with bromine. C3H7Br plus, and here's the other hydrogen that came off of there, and it bonds the other bromine. And that's a balanced chemical equation. There's 3 on the left, 3 carbons on the left, 3 on the right. 8 hydrogens on the left, 8 hydrogens on the right. 2 bromines on the left, 2 bromines on the right. Okay, so here's your equation. C3H8 plus bromine goes to C3H7Br plus HBr. And that's balanced. Now it says name them. This is propane. This is bromine. This is what? What's the name of this compound? I forgot all we just learned, huh?
Bromopropane?
Yeah, that's it. You got it. Bromopropane. Okay. And this is hydrogen bromide. Okay. So this is 1 bromopropane or bromopropane. You don't need the one that's on the end like that. And 2 bromopropane. Because you got to remember it can go to either one of the two. So C3H7Br could be bromine, could be here. That's right. It says list all products, all possible products. Okay. Or the bromine. And this is propane. Let's get all this structured here. Those are all hydrogens. So the bromine could attach to the first carbon and replace that one. Or the bromine can attach to the second carbon and replace that hydrogen. So this is attaching to the first carbon. This is attaching to the second carbon. That refers back to that on the structural formulas. Okay. So if we do lines for the reaction, we have propane, 1, 2, 3. We add bromine, we could add the bromine here, or we could add the bromine here. So we get 2 products, 1 bromopropane or 2 bromopropane. Okay. So you got to remember, you got to be careful where you're replacing it from. So let's replace this. We have butane now. Butane is 4 carbons, 1, 2, 3, 4. Okay, monochlorination. So we write the formula. We have butane is H what?
10.
H10. Why did I put 18? Okay, C4H10 plus chlorination, so plus Cl2 goes to C4H9Cl. We lost a hydrogen, replace it with a chlorine, plus HCl, hydrogen chloride. Okay, so can we get different products? We can attach the propane, the chlorine can attach to the number 1 position. It could attach to the number 2 position. And it's monochlorination, only one chlorine's attaching. Could it attach to the number 3 position also? Could it attach here? Yes or no?
No, it'd be the same as the second one.
Perfect, perfect. If it attached here, it'd be the same as attaching here because this would be the second one from the end. Okay, it's just the exact same thing, rotating 3-dimensional space. So there's only 2 possibilities. It could attach to the number 1 position or the number 2 position. So name it if it attached to the number 1 position. It would be 1
Chlorobutane.
chlorobutane or
2
Yeah.
chlorobutane.
2 chlorobutane. Those are your 2 possibilities. Let me get that out of the way so we can have some room for the relay. Okay. So there's your formula. Okay, C4H10 plus chlorine goes to C4H9 chlorine and HCl. And it can attach to the number 1 position or it can attach to the number 2 position. That one attaches there. So 1 chlorobutane or 2 chlorobutane. Okay. And let's do, we got one more. Let's do one more, then call it quits. Monochlorination of cyclobutane. Cyclobutane is 4 carbons, all connected. Yeah, that doesn't, it's not supposed to go that far. Okay. So what's your formula for cyclobutane? See what?
C4H8.
C4H8 plus, what are we going to add to this thing?
Cl2.
Cl2, and it's going to produce
C4H7Cl.
plus.
HCl.
Perfect. You got it. It's exactly what it'll produce. Okay. So there's your reaction. Okay. Now, this can form how many products? It can, this is your cyclobutane. It can connect at any one of those points. Okay. Is any one of those points going to make it any different?
No.
Right, because this is the same thing as this, which is the same thing as this, and the same thing with some attached on top. They're all the same. It's all 1 chloro cyclobutane. Okay, that's what it looks like. So chlorocyclobutane. You can put the 1 if you want, or leave it off. If it's 1, it's just there. So that's cyclobutane. That's what it'll produce. Okay. Is there one more? All right, let's finish this. It should just be one more. Bromination of pentane. Pentane is C what?
C5H12.
C5H12 plus bromination. So it's Br2 goes to C5H11Br plus HBr. Here's your balanced chemical equation. There's your pentane, bromine, goes to bromine and HBr. So now we got 5. I'll do line structures here. Let's do 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. You can put the bromine here, right? You get the bromine here. Put the bromine here. If we did on the other ones, it'd be the same thing. So we have three possibilities. The bromine could attach to any of those carbons because you replace any of those hydrogens. So the first one would be, what would the name of the first one be?
1-bromopentane,
Perfect. 1-bromopentane. Second one,
2-bromopentane,
and the third one,
3-bromopentane.
you got it. That's it. So the bromine can attach to number 1 position, number 2 position, or number 3 position. So you have 3 different products that will form with the monobromation of pentane. Talking about indoor swimming pools, a team of British researchers identified suspected carcinogen chloroform, CHCl3. Okay. Who wants to name that? Who can remember name the IUPAC name for that?
What do you mean, like just say the name?
Yeah, CHCl3. What's the IUPAC name like we've done in doing the naming? Because there's a carbon, hydrogen, chlorine, chlorine, chlorine.
Trichloromethane.
Perfect. Trichloromethane.
Oh my God.
3 means tri, so perfect. Trichloromethane. That's exactly what it is. Okay. Trichloromethane is chloroform and it's a carcinogen. Okay. There's other potential hazardous compounds called trihalomethanes that are produced in swimming pools in London, they were finding out. Okay. THMs, trihalomethanes, are products of chemical reactions between the chlorine that's used to disinfect the pool and the organic substances from swimmers themselves that come off the body. So chlorine reacts with stuff from your body that comes off to produce THMs. Okay. Skin cells are shed in the pool with lotions and other body care products. Okay. So organic molecules from these substances are chlorinated and they produce these trihalomethanes. They're very volatile components, so you can smell them in the air. Okay. In an indoor pool and an outdoor pool, they'll be evaporated and blown away by any breeze. Okay. In an indoor pool, there's less air circulation, so they tend to build up into high concentration in the air right above the pool. So these fumes are inhaled by swimmers and the trihalomethanes diffuse into the blood. Okay. Some of the fat-free production of the compounds include warmer water temperatures and larger number of swimmers, which means more organic material in the water. That's where we run into trouble with this. In some of the public pools, the levels of as high as 132 micrograms per liter. Now that's a lot higher than the normal. The normal is in drinking water is about 3.5 milligrams per liter. So it's 2, 3, 4. It's 7, 8 times what it's supposed to be. Actually more than that. Because 10, it's actually 20 to 60, 30, 40, it's about 40 times. About 40 times higher than it should be when you reach those levels. Okay. So on the experiments that they did, rats and mice who were exposed to this chloroform in the food and water, they developed liver and kidney cancers. That's what's considered a carcinogen. That's one of our chapters over a bunch of different carcinogens. Okay, so a 1 hour swim can increase the blood concentration of chloroform as much as 10-fold because they're breathing that air in right above the surface of the water. Okay. Studies have suggested miscarriages, birth defects, low birth rates might be associated with human exposure to chloroform. Okay. Further research needs to be done to have conclusions about what we can do to treat this out here. But that's why they ask you to shower before entering a pool, because of these THMs that are formed and the deadly effects they can have when they build up in high concentrations. They do recommend the amount of THMs be reduced as much as possible, but you got to maintain a high enough level of chlorine to kill all the bacteria in the pool. Okay, any waterborne infectious diseases. One of the ways to keep your pool water cooler and ask swimmers to shower before entering the pools to help reduce the production of the toxic THMs.